Good evening. It's 6 p.m. Eastern Standard Time, and this is the Randomizer. I'm Charles Schultz, and I'm the head of Schultz Laboratories in the Universe Science Center. And tonight's topic is going to be superatom, something a little different. We all know what atoms are. We know they're on the periodic table of elements. But sometimes when you want to do something, you need something that acts a little differently from anything on the table. And we now have some options, and we'll talk about that very shortly. I want to encourage the listeners and the supporters to go to schultzlaboratories.com or universesciencecenter.com, visit our main page, sign up for our classes and our lectures, sign up as a member. We have our Monday night classes starting at 9 p.m. Eastern Standard Time. Tonight is Meta World Lesson 5. We're going to talk about really advanced topics such as creating doorways between virtual worlds and reality. We've got some fascinating material to cover there. And every weeknight at 6 p.m. Eastern Standard Time, we do the Randomizer, where I talk about a randomly chosen science and technology term. Perhaps it's an inventor or a physicist. Perhaps it's a new material. You never know. Also, I'm thankful for all the people who have subscribed and become members. They're supporting our growth. We're adding more galleries and material all the time. Take your Oculus or any 3D headset you have, go in, walk around in our virtual galleries. It's a wonderful learning environment, and if you have a skill that you'd like to teach, we can set you up with your own classroom in the virtual space so you can teach people right there. Okay, so let's get down to superatoms. So you're building something and you need an atom that acts a certain way, and there's nothing on the table that acts that way. And yes, it's true, we're synthesizing new elements all the time. And right now we're up around 120 elements on the table. Normally in nature, you don't get past about 92 elements. That's the number for uranium. And even below that, there are a couple of elements that don't last very long, like technetium. It's not stable. There are no stable atoms of technetium anywhere, and they always break down. So there are a couple of holes in the table where you can make it, but it doesn't last long and it decays. But you'd say, well, if you're making new elements, why don't you use those instead if you don't have properties on the table you like? So let's think about that. You look at the periodic table, and every element has distinct characteristics of bonding energies and how many electrons are available. And this determines the properties of the chemistry of the things that you create. But sometimes you need something a little different. Now, one trick you can use, you can look at the columns on the table, and all the elements in a column, for instance, oxygen is quite reactive, and it has a couple of free electrons. Right down below it is sulfur, and the sulfur acts very much like oxygen in many ways, but it's a solid, not a gas. Carbon has 4 electrons on the outer shell, and it bonds very easily and makes almost all of the biological molecules in the world. And below carbon is silicon. Well, silicon also has 4 atoms that can bond. It's very much like carbon, but silicon's bond energy is different, and it doesn't work quite the same way. So you can sometimes go up and down in a column and get a slight difference in something, and that's useful. And people would say, can't we use any of the new elements we have? Well, no, you can't, and here's why. We can predict what their chemical properties would be, their bond energies. We know how many electrons they have, but the problem you run into is the newer elements are very dense and they're not very stable, and they would break down very rapidly. So 2 problems with using the new elements and trying to exploit their chemical properties. A, any compound you made with them would be radioactive, and that in itself is a danger. And B, they don't last long enough to do you any good. They'll break down in a few milliseconds in most cases, a few thousandths of a second, and you got nothing. So you don't want that. So here you are making some new wonderful thing, and you need a material that acts in a certain way. What do? Well, it turns out that elements come together in different ways sometimes, and the perfect example is carbon. Now, you probably haven't heard the word allotrope, but an allotrope is a different form of something, and carbon is a great one to work with. Everybody knows that carbon can be found as the soot in a candle flame, the black, fluffy, soft stuff. Okay, fair enough. Carbon also can be found in a mineral form it's crystallized, called graphite. And graphite is a very interesting and useful material for many industrial processes. Any pencil has graphite in it for the so-called lead. In fact, what's in a pencil isn't lead at all. It's a mix of Bavarian clay and Madagascar graphite, which has been ground up to a fine powder. They literally take the graphite clay, make it into black clay, and fire it into long, thin rods, and that's the graphite in your pencil. So carbon can be in soot, which is a soft form. That's one allotrope. Carbon, still just element carbon, can be as a crystal called graphite, which is a soft, slippery black material. Carbon has a third well-known allotrope, diamond. The crystal structure is just a little bit different. It's bonded differently, and it gives the material the hardest binding strength, or I should say it's the hardest crystal you're liable to find in nature, diamond. There is a fourth allotrope for carbon. That's called Buckminster fullerene, and it looks like a little geodesic bubble, like a soccer ball, and it's made of carbon atoms only. So these are four allotropes of carbon. Now what's interesting about this is each of these forms acts differently electrically and chemically. So because of this, we have a hint here that maybe we could take individual atoms with certain properties and combine them in some way and create a completely different fake atom. And what this cluster of atoms that acts like a single atom with properties similar to those on the periodic table is called is a superatom. Now, what do you do with a superatom? Well, first of all, you can take, for instance, aluminum metal, and you can vaporize it by running an extremely high current through a thin aluminum wire. And this is done normally in an atmosphere of an inert gas such as helium or argon. So you vaporize the aluminum and the particles, the atoms, spread out, and when they cool, they tend to cluster together. Now this is the interesting part. When the atoms cluster together, they tend to do it in such a way that follows something known as magic numbers. It's kind of like you can take four little balls, tennis balls, and stick them together into a perfect tetrahedron, a little pyramid with three sides. That's a cluster based on a magic number of atoms fitting together. You could stick them all around there and get 8. Okay, that makes sense. You can build on these clusters in a certain way and they'll become stable. And this is a crystal that often could not be repeated forever, but locally it works. These clusters often have properties that are very different from the initial atom. So if you were to take aluminum and vaporize it in argon or helium, and you were to interact a gas containing iodine with it, a very funny thing happens. The aluminum, in clusters of 13 atoms with a single iodine attached, take on radically different properties. This is because when those atoms all fit together, the electrons in the outer shells form a sea of electrons around the entire crystal. And so these electrons can act like the outer electrons of an atom sometimes. That's a superatom. So for aluminum 13 with the iodine, a funny thing shows up. Aluminum, as I stated, is very reactive with oxygen. If you have a piece of aluminum metal and you look at it, you'll notice it looks like it doesn't rust. But what's happened is oxygen in the atmosphere has attached to it and formed a thin glassy layer of aluminum oxide. This is the same stuff that sapphire is made out of. It's called corundum. And this compound is extremely hard. Because of this, if you took a piece of aluminum and tried to polish it up like a mirror, it wouldn't work because the oxygen in the air will have created these little hard inclusions that will grind in and mash into the surface, and you won't get a smooth coat. They have to immerse it in water and fill it with squid ink, India ink, in order to polish it, and then they can get the job done. But in the air, it'll never work. But now, when you have these clusters, these superatoms of aluminum with 13 aluminums and 1 iodine, it acts incredibly differently. It does not react with oxygen. It's stabilized and it acts like a halide. And a halide is a compound with a halogen such as fluorine or chlorine or bromine in it and some other material, usually a metal. So the aluminum acts entirely differently chemically when it's in these little clusters of superatoms. So now, this means that we have a different material, and if we can bond it together with other pieces, we can make something that may have that property throughout. So many different elements will form superatoms. For instance, aluminum 7 clusters act like the semiconductor element germanium. Germanium is similar to silicon. It was often used for semiconductors in times past. It's not so popular today, but it's actually a very good material to use. When you have aluminum-13, it can act a lot like chlorine under the right circumstances. Gold, gallium, rhenium, and other elements can also form these superclusters. Platinum shows a very interesting property. Everybody's familiar with ferromagnetism, which is the property that allows a magnet to stick to a piece of steel, like that. Well, this is showing ferromagnetism, and this magnet will hold it. Some materials have other properties of magnetism called paramagnetism, which is a weakly attracting form of magnetism, or diamagnetism, which is actually repulsion. Carbon will repel a very strong magnetic field sometimes, and it depends on its form. Well, platinum is weakly diamagnetic, which is a weak attraction to a magnet. But strangely, clusters of 13 platinum atoms become incredibly paramagnetic, very paramagnetic. So if you could take your platinum metal, form it into a vapor, condense it into platinum-13 clusters, and then form that into an object, its paramagnetic capabilities would be incredibly strong compared to regular platinum. So the trick here is to find ways to bind those superatoms together so it doesn't destroy these new effects. One of the things that might come out of this, and this is what's most interesting, a lot of these superatoms actually show in clusters or sheets or structures the property of being tunable. In other words, by using some external influence or doping it with another material, you can alter the properties the way you would like. This is very interesting. One of the things they've discovered, particularly in graphene, is if you take a sheet of graphene and another sheet of graphene and you rotate it at an angle before you put it together, you've created effectively the same sort of process. The distances for the electrons to jump and the energies involved change very differently. You end up with a material that has novel properties that no semiconductor has by changing the gaps and distances between the electrons in the crystal structure. So superatoms give you the ability to control some of the properties of your materials. Now, what was that leading to? Well, with our work in nanotechnology, we're learning how to put things together in new ways, and superatoms could be essential building blocks for creating new materials. Imagine something that acts like a plastic, is soft and malleable, but on command hardens up like steel. This would be a very novel property with a lot of uses. And if you could turn that property off and make it soft again on command, you'd have a mutable property material that you could literally make soft, create a mold, harden it, pull it off, soften it up again, and reuse it. There's one possibility for what could be done with some of these properties if we can tune them on the fly. Imagine a material that acts like a glass, like an insulator, but that at the throw of a switch becomes a conductor like a metal. We do have semiconductors that can do things very similar to this, but imagine a bulk material you could do that with. We could see a lot of changes in material sciences by incorporating these in composites. So the properties of strength and flexibility can be given other properties such as being able to become a conductor on command. Imagine a cable that can be programmed into being 30 parallel wires or one large wire, just with the throw of a switch or the inclusion of a little software. We're reaching a stage where matter is becoming a controllable form, something that we can alter in ways with software or chemistry or heat or light. Here's an example that also exists in nature that you're probably not aware of. Many times, when we study seismic waves traveling through the earth, we can locate things such as hot spots where magma is moving in the mantle, and places where the heat flow changes rapidly. An area that has been expanded due to heat suddenly becomes cooler, and it doesn't make any sense. What happened? Well, it turns out that there are certain minerals that, when highly compressed under the weight of millions of tons of rock and the heat inside the earth, become absolutely different sorts of compounds. Some of these minerals change state in such a way that in one form they block the flow of infrared or heat. And so, if they surround an intrusion of magma underground, they keep it insulated like styrofoam, and the magma heats up and it traps the heat there and it's expanded. And then one day, that area begins to shrink. For some reason, the heat is being lost. It turns out that under the proper conditions of temperature and compression, some of these minerals turn on like a window and suddenly become transparent to infrared and allow it to blow right through. So here we have a switchable insulator that allows itself to be switched from stopping the flow of infrared to allowing it to flow through it like a piece of glass. So we can imagine these properties would be very useful, but we certainly can't put millions of pounds of pressure or thousands of degrees of heat on something to make that happen. It's not practical on the surface. Superatoms and nanotechnology combined may give us the ability to create these novel materials with properties that can be switched, thus changing a lot of the things that we do in the world into simpler forms. So imagine superconductors that can be turned on and off without having to be chilled with liquid nitrogen. Imagine glass that become a metal or back to a glass, or materials that change their hardness or their density. So this is just a sample of what might be done without having to go to the trouble of create completely new elements that are radioactive and wouldn't do the job in the first place. So superatom is the term, and if anybody has any questions about it, the floor is open, and I think that this is a fascinating subject, and just wait and see what they do with it in times to come. I do expect to see some huge developments in the near future. Meanwhile, do go to schultzlaboratories.com or universesciencecenter.com, sign up with us, become a member, support our growth and development, sign up for our classes. Meta World is in progress, lesson 6 tonight at 9 p.m. Eastern Standard Time, lesson 5, I'm sorry. The next course will be on robotics. I'm putting together something that I think you'll be fascinated by. So, thank you for joining us tonight. I don't see any questions on the floor, but I think superatom is a fascinating concept and something you need to follow in the news. Keep your ear to the ground and keep your eyes open. Meanwhile, I have a quotation for you, and this reminds me of politics in general. This was a randomly selected quote, I must admit. And it's Jeremiah 6:13. For from the least of them, even unto the greatest of them, every one is given to covetousness. And from the prophet even unto the priest, every one dealeth falsely. That seems to describe a lot of what's happening in our world today, but don't be faint of heart. Take faith in the fact that things are going to work out. Stick in there, people, and make the world a better place. And thank you for coming in tonight. We'll see you later.